Today, I shall take up the last topic that I have planned to consider under the heading Advanced Quantum Mechanics. Today, we shall discuss perturbation theory. There are very different variations of the perturbation theory. We shall consider the simplest amongst one, which is known as time-independent non-degenerate perturbation theory. Consider a system. For example, we are considering a harmonic oscillator system. The harmonic oscillator system, the Hamiltonian is p operator square by twice m plus half m omega square x operator square, and we know the exact solution corresponding to this Hamiltonian. That is, we know that a0 operating on psi n 0 is en0 psi n0, where they are related to Hermite polynomial e to the power minus alpha x square by 2 hn of alpha x, and en is n plus half h cross omega. So the system is exactly solvable, and we know this. Now, if we consider the Hamiltonian to change from h0 to h, where h is h0 plus some additional term, as for example, where h prime may be some constant a times x to the power say m, where m could be 1, 2, 3 and anything else. But if we choose m to be greater than, if m is greater than 2, then the problem is no more exactly solvable. If m is 0, then we can add a constant term to the Hamiltonian. If m is 1, then this term can also be accommodated, and if m is 2, this part may be modified to accommodate square term. But when m, say x, the perturbation is x cube or x to the power 4, the problem becomes exactly solvable. So we cannot solve the problem exactly. But if we are dealing with situation where this h prime part is small compared to h0, by small we means we calculate the expectation value of h0 and of h prime, and it is found that the expectation value of h0 is much greater than h prime. Then we can consider this part to be a small additional term which is added to the exactly solvable Hamiltonian, and we call it a perturbation. By perturbation we mean that the additional term is small enough so that the overall structure of the system which was described by Hamiltonian h0 remains the same. As for example, if we put an atom in a magnetic field, then the electron will have a helical tendency or the electrons will have a tendency to follow a helical path due to the action of the magnetic field. But if the magnetic field is not strong enough, then the electron will continue its motion about the nucleus in a closed orbit, but the orbit will be slightly disturbed from the original orbit, that is the orbit that the electron was following before the setting on of the magnetic field. But if the magnetic field is strong enough, then the electron breaks its bondage with the nucleus and follows a helical path. In that case, the additional term cannot be treated as perturbation theory. So the basic understanding of the perturbation theory is that the additional term has small effect on the system, that is to say that it cannot change the dynamics of the system drastically. It only causes slight modification to its wave function and energy values. So with this we consider a system which before perturbation we call it exactly solvable system. The Hamiltonian is H0 and the eigenstate is psi n0 with energy En0. This is unperturbed state. Unperturbed state, and this satisfies H0 psi n0 is equal to En0 psi n0. This system, this could be a system of helium atom. H0 may be the Hamiltonian of the helium atom, and psi n0 is the wave function of the helium atom in presence of any external disturbance. In that case, the problem is not exactly solvable, that is not an analytically solvable problem, yet we assume that we know the wave function and the corresponding energy with sufficient accuracy. Now, with the switching on the perturbation, the Hamiltonian becomes H0 plus H prime, and the wave function also changes. We expand this in a power series of a quantity lambda, so we call it this is the changed Hamiltonian. The wave function correspondingly, the nth state wave function now correspondingly changes to phi n0 plus lambda, phi n1 plus lambda square, phi n2, etc. These are the orders, and correspondingly energy becomes En is equal to En0 plus lambda En1 plus lambda square En2, and so on and so forth. And we assume that this new Hamiltonian satisfies the condition. This is the perturbed state. Perturbed state. And where the expansions are given as above. So we use these things to write, this is H0 plus lambda H prime operating on psi n. For psi n we write psi n0 plus lambda psi n1 plus lambda square psi n2 for energy and for wave function now we first consider the term independent of lambda. This is obtained from this psi H0 psi n0, and then come to the term containing lambda. So this is obtained when H0 operates on this, H0 operating on psi n1, and this operating on H prime operating on psi n0. Then we have lambda square term. Lambda square may appear when this operation this, so H0 operating on psi n2, then this operating on this, psi n1, and similarly higher order terms. And on the right hand side we have, when this operates on this, we get En0 psi n0 as the coefficient of lambda to the power 0. Then when this operates on this and this operates on this, we get term containing lambda. So this is En0 psi n1 plus En1 psi n0 plus lambda square. Lambda square term arises when this operates on this, so En0 operating on psi n2, this operates on this, plus En1 psi n1, and when this operates on this, En2 psi n0 plus higher order terms in lambda. This relation is an identity in lambda, that is, it is valid for all values of lambda, and if we since this is an identity, the coefficient of every power of lambda on the left hand side will be equal to that on the right hand side. So the coefficient of lambda to the power 0 gives us H0 psi n0 is equal to H0 psi n0 is equal to En0 psi n0, which was our starting relation. The coefficient of lambda to the power 1 gives H0 psi n1 plus H prime psi n0, so sorry, this is n psi n0 is equal to, this is on the left hand side, on the right hand side we have this En0 psi n1 plus En1 psi n0. The coefficient of lambda square gives us H0 psi n2 H0 psi n2 plus H prime psi n1 is equal to, on the right hand side it is En0 psi n2. In general, we could collect the coefficient of lambda to the power k to get H0 psi nk plus H prime psi nk minus 1. On this side we have En0 psi nk plus En1 psi nk minus 1. Ultimately the term will be Enk psi n0. Now this psi n0 is the unperturbed wave function, and En0 is the unperturbed energy and H0 is the unperturbed Hamiltonian. In that case, this is the first order correction to the wave function. This is the original wave, this is the original unperturbed wave function. This is the first order correction to the total wave function. In this sense, it is the first order correction to the wave function, and this is the first order correction to the energy. So if we confine ourselves to the first order theory, then psi n will be this plus this, and energy will be this plus this, and this is valid for all values of lambda. We assume lambda to be 1 because our original Hamiltonian was H0 plus H prime, which we use written as H0 plus lambda, so lambda has to be 1. So we can get the correction to the energy and the wave function. If we were not satisfied with the first order theory, then we are to go for the second order theory, in which case the second order correction involves the unperturbed energy and unperturbed Hamiltonian, unperturbed energy, unperturbed wave function. Sorry, this term is 0 1, this should be 2, this is 0. Please note the correction. So the second order theory includes unperturbed Hamiltonian, unperturbed wave function, unperturbed energy, first order correction to wave energy, first order correction to wave function, and the second order correction to energy and wave function. We shall confine ourselves to first order theory only. So our starting point, we will solve only this part of the equation, and rest will be treated in still higher classes. So in first order theory, in first order theory, we have this is the theory, and our aim is to find out E1 and psi1. Firstly, we shall aim is to find En1 and phi n1. Firstly, we recurse this equation in Dirac's notation. In Dirac's bracket notation, this equation becomes H0 operating on psi n1 plus H prime psi n0 is equal to with the original H0, the unperturbed set, we rewrite this as H0 minus En0 operating on psi n1 plus h prime minus en1 operating on psi n0 is equal to 0. We multiply both the terms of y by phi n. Phi n0, and this is h0 What happens to this equation? We know that h0 phi n0 is equal to en0 phi n0. If we take the Hermitian conjugate of it, then this equation becomes psi n0 hn0 dagger, which is hn itself, and this is en0 being real. So if we take it, or we get psi n0 h0 minus en0 is equal to 0. That is, this part is 0. And we divide these two terms to get en1 is equal to psi n0 h prime psi n0. Let me explain the passage from this term. This is 0, so this equal to 0. We divide it into two terms. One is this, and this. So this is the right hand, taken to the right hand side, and En being a scalar and the state to be assumed to be normalized. So this. When we sandwich this between these two, it is being a scalar taken out. So we have simply psi n0, this is due to normality 1. So this is the expression for the correction. So first order correction to energy, first order energy correction. So we still have this. So we get the correction to the first order energy. Now if we want to know what is the wave function, so first order wave function, we write the first order wave function in a state n as summation over k. This is a n k of force. Let me explain the term. The Hamiltonian, all the eigenfunctions of the Hamiltonian H0 forms a complete basis. So any other wave function can be written as a linear combination of the unperturbed wave function. So we have written this. So this is the representation of the state psi n1. So there is a signature of the state n. This is the summation index, and it is the first order correction, so 1 is over there. Note that this summation over k is sum over all the discrete states and integration over all the continuous states. So in some book it prefers to write it like this. So that means it is summation over discrete states and integration over continuous state. However, we shall keep this symbol simple and we write it like this. And we use this in this relation. So we have this relation. When use this, we get H0 En0 summation over K ANK1 psi K0 plus H prime En1, which is known to us, sin N0 is equal to 0. We pre-multiply this equation by psi, we pre-multiply it by psi M0. So we get when this operates on this, we get, let me take this sum out, sum over K is out, ANK1 is taken out. When this operates on this, we get EK0. So this is psi M0, this is EK0 minus En0 times psi K0. This 2 gives you the delta function Km, and coming to right hand side, this term. We get, this is En1, and this is a dot product between state N and M, so which is a delta Nm is equal to 0. And this also leads to a delta Mk, and when we perform the sum over K, we get only the term corresponding to K is equal to M. So we get ANM1, then we have EM0 minus En0, and if we take M not equal to N, this term goes, and we have plus which allows us to determine ANM, and when we use this value of ANM, the wave function is known. So we have shown the procedure that enables us to find out the correction, first order correction to energy and wave function. Today we shall apply this theory to very simple cases. Our main objective will be to find out the correction to the energy. So this will be our starting point. Let us write that the first order correction to energy is En1 is equal to psi n0 h prime psi n0. As simple as this. The matrix element of the perturbation part of the Hamiltonian with respect to the unperturbed states. Consider a potential, one-dimensional potential P of x is equal to 0 for x less than a greater than 0 and infinity otherwise. We know the unperturbed state in this case psi n0 is 2 by a sine of n pi a x with energy En is equal to pi square h line square by 2 m s square n square. This is psi n0. And n ranging from here, n is 1, 2 onwards. 0 is excluded. Let us consider the perturbation h prime is alpha x is the perturbation. So what will be the correction? The correction of energy will be En1 is equal to psi n0 h prime psi n0. So writing in this form, this is alpha, and from this wave function 2 alpha a, 0 to a, integration x sine square n pi x by a dx. This can be written as alpha by a, 0 to a, x twice sine square means 1 minus cos of 2n pi x by a dx integrated from 0 to a. It will have two terms. This part will contribute nothing, so the correction will be alpha by a x square. So this is a square by 2 is the correction to the energy. And so this is alpha a by 2 is the correction to the energy. Similar situation can be applied. Consider such an example that the potential is infinite between 0 to a. The potential is infinite, and we have put a small bubble on it, so that this may extend from A1 to A2, where both A1 and A2 are less than A, and this part is small perturbation V0. What will be the correct change in the energy eigenvalues? This may be simple problem of interest which we can consider. Now we come to some real life problem, the harmonic oscillator problem. We shall not go into the detailed calculation, but we shall just indicate the changes. The harmonic oscillator problem, we may consider that h prime is equal to AZ, AQ, and we consider an entire discussion in dimensionless form Q, in which case psi n0 is actually, apart from normalization constant, is e to the power minus q square by 2 and h n q. Now when we are applied with such a perturbation, this is psi n0 h prime, psi n0 is the correction. So in all we have A taken common. This is the state n, q, n. We know that this is 0 because this is the expectation value of the position of harmonic oscillator, which is 0. So this is 0. If we consider the perturbation to be x square, then it will have certain term. If we consider the perturbation to be is equal to bq square, then the corresponding change in energy, first order energy, will be b in q operator square n, and we know that this value is non-zero. Basically this is proportional to 2n plus 1. This is the correction. If we have cubic potential, perturbation is cubic perturbation, h prime is cq cube. In this case we are to calculate en1, this is n q cube n. Then we may use our earlier notation about earlier calculation regarding the matrix element, that is m q n. This is delta n plus minus 1 n, and we know that m q square n, this has 3 contribution, m is equal to m. So m is equal to n, contribution is m is equal to n and n plus minus 2. There are 3 contributions. We can use this. Another concept that will be very helpful is the completeness of the wave function. Earlier we have talked about the completeness of the wave function. Completeness, we argued that the completeness means this thing: sum over k is equal to an identity operator of the appropriate dimension. So we sandwich this operator, we rewrite this as sum over n q square n, and we sandwich this one within n q k q square n, q square n. We know that this will contribute when k value is plus minus. This contributes to non-zero value when for n is equal, k is equal to n plus minus 1, and this contributes when k is equal to n or n plus minus 2. So there is no common value of k coming from these matrix elements, so the result is 0. If we could apply the same theory to a perturbation going as q to the power 4, we see that h prime is equal to d q to the power 4, and the correction is n h prime n, which is d n h prime sorry, this is q to the power 4, which is written as q square times q square. This is written as d n q square operator, and we sandwich the idea completeness relation between this. So this is d summation over k n q square k q square n. We know that this k contributes when k is equal to n and n plus minus 2. Same thing is valid for this. So there are three contributions. Actually, there will be three contribution d, and then we have n q square n q square n. This is the first term. Then n q square n plus 2 q square n, and last term is n q square n minus 2 . These are the Hermitian conjugate of each other, so we can write it as d n q square n whole modulus square plus n q square n plus 2 square n q square n minus 2. These are the three terms, and from your knowledge of harmonic oscillator, we could use the values of these matrix elements to find out the correction to the perturbation when they have perturbation Hamiltonian is this. In the next class, we shall apply this perturbation theory to the evaluation of the relativistic correction term of hydrogen atom.